Alright everyone, welcome back. And if you're new to this channel, basically I just come up with non-elementary integrals and then solve them, and then I explain them very in depth. So that's why you see the video is so long, because I want to make very non-beginner friendly problems. Like, I want to give them a beginner friendly explanation, but that obviously takes time. Anyway, I haven't uploaded in a while because I've been busy with school, and also frankly as I've learned more math and more techniques on how to approach these kinds of problems, I've found that less and less integrals actually amuse me, or there's fewer and fewer that I consider worthy for a video. But I came up with this one, and solution's nice, checked all the boxes. Yeah, so we're back. I think that's all of an introduction I can give. So let's start looking at the problem. So basically it's got 4 parameters, which I think, I'll tell you in a second, I like parameterized problems. But basically you got 4 of them. You can, like the numerator, this cosine term, I had to add in after trying to solve a similar, like, basically I came up with the integral where it's just this without the cosine, but then it didn't work out. So then I backtracked, figured out what term I could add in order to make this work, in order to make the problem solvable, and this was it. And then in the denominator, you've got all the degrees of freedom you could possibly want. Whatever constant here, whatever constant here, whatever constant, or okay, some specific kind of angular frequency there, and then you can just raise the denominator to whatever whole power you want. Anyway, the reason I like the parameterized problems is because let's say you have just a regular definite integral with no parameters. Then practically speaking, nobody cares what the exact value is if you can just get like a very good numerical approximation. Excuse me. But when you have all these parameters, or even just one parameter, finding a closed form becomes so much more valuable, because then computers don't have to symbolically evaluate it. And like the numerical process for like each individual case becomes a lot simpler, because instead of doing like a Riemann sum a bunch of times, all you have to do is plug in values into the closed form, which is a lot more efficient. So I think you get, like, it's a lot cooler to have an exact form, or like a closed form with parameters, and it's a lot more efficient, like, practically speaking. So yeah, that's why I stick with these. Like on my channel, there's plenty of non-parameterized ones, but when I find ones like these, I really like it. Okay, yeah, it took me a while to come up with, and after a lot of playing around in Wolfram Alpha, I established these have to be the conditions, the restrictions on our parameters. So n, like I said, has to be a natural number. Well, I said it's a whole number, but like, I put it in the denominator. You should figure it's a natural number. Yeah, so 1, 2, 3, whatever. Plug that in for n. Omega can be any natural number divided by 2, which, if you think about it, that includes, 1/2, 3/2, 5/2, but that also includes all the natural numbers themselves, because 1 is 2 over 2, and 2 is 4 over 2, blah, 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 blah. So, yeah. And then there's no restrictions on alpha or beta except this, which this should be pretty intuitive if you look at the denominator, because sine squared will always be between 0 and 1, and I just replace that with an r, and basically we just don't want that equal to 0 at any point. Which makes sense, right? Because that would make our function discontinuous. So, yeah. And like I said, alpha, beta could be complex. They don't have to just be strictly real. Yeah. Okay. One thing I need to do before I actually start solving the integral is clarify something about omega. So, omega, once I actually start solving the integral, I have to treat it as a whole number. Now, obviously, this contradicts what I put up here, because omega could be 1/2, 3/2, whatever. So I'm looking to find, I'm first going to find a relationship, and well, derive that relationship between the fractional values of omega and the whole number values of omega, because I want to be able, like I said, I want to be able to treat omega as a whole number. So without further ado, let's start with that. So let's define I of omega equals k over 2, where k is a natural number, So that covers basically all the possibilities that omega could be, right? What did I say? So yeah, just define it like this. I'm not including the other variables in here just because they're all going to stay the same. I'm not actually plugging anything in. So all we have to do is sub in this for omega. So just rewrite this. Oops. Okay, so that's what the integral looks like. Now, I'm going to rewrite this as not the integral from 0 to pi, but the integral from 0 to 2 pi minus the integral from pi to 2 pi of the same thing. Okay, now, for this one, we can just do a substitution. Theta goes to 2 theta. Now, just a preface. Okay, that's actually kind of ugly. You'll see me, well, not just in this video, but like in other videos, past and future, using substitutions like this, where I use the same letter for the old and new variable. But it doesn't really matter as long as you clarify what's your old and what's your new variable. But the utility of this is that oftentimes during a substitution, I want to compare the old version of the integral to the new version of the integral, like post-substitution. And it's a lot more difficult to, visually analyze it when the index variables are different, because the index variables don't matter in a definite integral. But obviously if I've got theta and x, in two different integrals, it's going to be difficult to compare them optically. So by using the same letter, at least you can see the similarities a lot easier. So that's basically the point. And then the differential, so this is old theta, this is new theta, by the way. So the differentials will just give us old d theta, will give us 2 times new d theta. So we just get an extra 2. So this is just going to equal 2, integral now the bounds. Okay, so old theta equals 2 new theta, so new theta equals old theta over 2, so this becomes that. Then we just plug in 2 theta for wherever our old theta is. Now I'm going to cancel out the 1/2 into k over 2 with the 2 coming from the 2 theta, so that's just k theta. Oops, and then I'm going to do the same down here. Okay, nice. Now, compare this to this. That is just the exact same form of the integral we have, but with omega plugged in as k, which we know is a whole number, because we defined it that way. So, this right here is 2i of omega equals k. Alright, and then this one, I'm going to use the substitution theta goes to 2 pi plus theta. So again, old theta going to new theta. And then the differentials stay the same just because, this is a constant times theta, and it's the same constant on both sides, so derivatives are fine. Okay. So, and then the bounds, it just means new theta is old theta minus 2 pi. So that means we're going to have this. So pi minus 2 pi is minus pi, and that's 0. Now I'm going to do the same thing. I'm going to push the 1/2 from the k over 2 into the 2 pi plus theta. So that's just going to give us pi plus, wait. You have to put the k. K, and then one more. And this, and then in the denominator, same thing. It's just going to be k times pi plus theta over 2. All this to the n. Okay. Yeah. All right. So now we have to do some, we have to look at this. So let's look, basically, we're going to keep this n minus 1 by itself. Like, we don't want to split up the n and the 1 because we want to make it look like our original integral. So that means we're going to have some multiple of pi plus everything else multiplied by theta over 2. So let's see what the multiple of pi next to it is. So we have a k, which is a whole number. Then we have n minus 1, which is a whole number. And we have 2. So that means the 2 makes everything else even. So that means we're going to have an even multiple of pi. Or in other words, a whole multiple of 2 pi plus, theta over 2 times all this. But as you know, rotating any number of times, or rotating by 2 pi any number of times doesn't change anything. So that means we can pretty much ignore the pi's presence. And then we can rewrite k times theta over 2. Just basically move the 1/2 to a different place. So instead of k times theta over 2, we write k over 2 theta. Yep. And then for sine, it's a little bit different because we don't know for sure the coefficient of pi will be even. But if it is even, then obviously the sign will stay the same. And if it's not, so that means if it's an odd multiple of pi, that means when you start at 0, no matter what, an odd multiple of pi will land you here. So since our angle is still positive, like we're not subtracting an angle, we're adding an angle, it means sine is still going to go counterclockwise, like this. But since sine is the y component, it means it's going to be negative. Like immediately after pi, sine is going to be negative. But it's still going to retain the magnitude of the regular sine values as if it started at 0. So that means sine of an odd multiple of pi plus an angle is just negative sine of that angle. But since it's sine squared, you can get rid of the negative because it cancels. So it's the same thing. We basically can ignore that the pi exists, and then we'll do the same rewriting trick as k times theta over 2 is the same thing as k over 2 theta. Then raise that to the n. Now we have to do one more thing. These bounds are a little ugly, but notice that cosine is an even function. So cosine of minus x equals cosine of x. And here, sine squared. So sine is typically an odd function. Well, sine is an odd function, but sine squared is an even function. So that means our entire function is even in terms of theta. So that means the integral from minus pi to 0 is the same thing as the integral from 0 to pi by symmetry. And now, compare this to where we started. This is just our integral with omega equal to k over 2, right? And keep in mind this is subtracted. So that just means that is minus I of omega equals k over 2. Okay. Now we can erase that. But now remember that all of this came from where we started, which was I of omega equals k over 2. So from I of omega equals k over 2, we got the omega equals k part and another copy of the omega equals k over 2 part. So now we can just solve for I of omega equals k over 2. Put this over here, you get a 2, cancel out the 2's, and what that tells you is that I of omega equals k over 2 is the same thing as I of omega equals k, which we know k is a whole number. So there is the relationship I was looking for, that now we can treat omega as a whole number, because it's not just that the omega equals k over 2 case is related to the omega equals k case, but it's just directly equal. No like scaling, nothing. It's just straight up equality. So that's very useful. So now we can sort of assume that any fractional omega can be treated as just the number in the numerator. Yeah. So I will make a little note just so that nobody forgets. Okay, let me get some water because that's a lot of talking and there's plenty of more to come. Okay, now we can actually get started solving the integral here. So, for those of you who are experienced with these kinds of problems, you probably know where we're going already. For those of you who aren't, the first thing you should do in problems like these, so also I will preface, in case anyone doesn't know the definition of non-elementary, it just means you can't find the antiderivative and just evaluate at the bounds. Because it's just not possible. So here is one of those cases. That's why these would be integrals I like doing, because you have to use other math basically to solve it. So anyway, the first thing you should do is, for someone who's inexperienced, is try to see if there's any relationship between the numerator and the denominator. So, but unfortunately, notice that the arguments of the trig functions are just completely different. Okay, sure, you have omega theta similarity, but this 2 times n minus 1, is destroying any chances of a clever substitution to, find the derivative of this or something, So that's never going to work. And there's really not much else you can do. And especially when you have such a nasty problem where where you're raising the denominator to a power, just any arbitrary power, only makes things more complicated. But when in doubt, basically, when you run into a problem and you don't really know what to do, if there's a way you can complexify it, that is usually a good step. And especially when you have trig functions, the steps can become a lot easier, and it should be sort of your first gut instinct whenever you see unsimplifiable trig functions. It should be to just express them in terms of their complex values or their complex representations, and then go from there. So that's exactly what we're going to do. Now, even experienced integrators, probably the first thing they're going to think is to convert this cosine into the real part of e to the I times 2 times n minus 1 omega theta, which makes sense. That's basically where we want to go. But that actually will mess you up and make the problem unsolvable. So basically you have to have a little bit of foresight to hold off on substituting for rewriting the cosine. Even though, yes, the idea is to use complex exponentials, but be careful. Don't get trigger happy with changing the cosine. So in order to make it obvious what we actually want to do with the cosine, I'm going to start off by rewriting the denominator in complex form. So yeah, the idea is to first rewrite this in terms of complex exponentials, because that's really all we can do. So recall sine x equals e to the ix minus e to the minus ix over 2i. Our x here is just omega theta. And then if we square it, this is just going to give us e to the 2i omega theta plus e to the minus 2i omega theta minus 2. That's the cross term. And then 2i squared is minus 4. Okay, nice. So that's sine squared. So that means our denominator will be alpha plus beta times all that. I'm just going to make this. Okay, so this will be integral from 0 to pi. Again, leaving this cosine b for now. Okay. Alpha is beta times this. Nice. Okay, this is a rather pesky -4. It's just messing things up. So I'd like to be able to multiply the inside of the nth power by -4 to cancel that out. But that means I'd have to multiply the entire denominator by a -4 to the n to be able to squeeze it in here. But that also means I got to multiply the numerator by the same thing so that I'm not changing any values. So this is like this. Okay. So multiply -4 inside here. That's -4 alpha. I'm just going to keep the beta outside. And the -4 just gets canceled in here. And all that to the end. Okay, that's where we're at. Now, I could have mentioned this earlier, but still safe now. Basically, the point of using these complex exponentials is that there's this very powerful theorem, like for those of you who don't know, in complex analysis, called the Residue Theorem, which will let us evaluate a contour integral, and give us some nice values in the form of something called a residue. And basically, the way residues work best is when you have a polynomial in the denominator. Now, we obviously don't have a polynomial in terms of the variable we integrate with respect to, which is theta, but the objective is we can try to get a polynomial in terms of e to the 2i omega theta, and then we can use a substitution later to get it into just like a regular looking polynomial, because then the residue theorem will let us use the discontinuities of that function to give us some nice values. Yeah, okay. So that means if we're looking for a polynomial in the denominator with the variable being e to the 2i omega theta, we can't have e to the minus 2i omega theta because that's the reciprocal of it. That's not like something you see in a polynomial. So in order to clear that up, we would like to multiply the entire inside by e to the 2i omega theta so that this would at least become a constant. So that means we need an e to the 2i omega theta to the n in the entire denominator so that it can slide in here. But that also means we need the same thing in the numerator. Sorry. Okay, so this would still give us -4 to the n. Integral from 0 to pi. All this stuff. And then we still have to put, e to the 2i omega theta to the n, just you can put the n in the exponent, because exponent rules. Okay, so now we can multiply the inside by e to the 2i omega theta. So that's this. Now I am going to distribute the beta. Oops, not an n. This just becomes beta because it gets canceled. Oh, 2 beta. This to the n. Okay, so that's our new denominator. Pretty nice. You can see it's already looking like a polynomial in terms of e to the 2i omega theta. Okay, what next? So let's first collect these. Let's rewrite this because we have like 2 of the same term here. So that is going to give us beta times e to the 4i omega theta minus 4 alpha plus 2 beta, just because we had a -4 alpha minus 2 beta times e to the 2i omega theta. And what do we have? Plus beta. All this to the n. Okay, nice. So now remember I mentioned that eventually we want to make a substitution to make e to the 2I omega theta are like some new variable. So when it comes to complex numbers, you generally use z. So I'm just going to use z equals e to the 2I omega theta. I'm not actually substituting yet. I'm just trying to demonstrate what we actually need before we proceed. So, but that would mean dz equals 2I omega e to the 2I omega theta. Okay, but we can't do the substitution yet because we still haven't complexified our cosine, but we're almost there. But first, we need to get this as part of our differential element, right? Because we already have the d theta. Oh, whoa, forgot. D theta. Okay, so we need to have this times d theta in order to get our dz. So all that means is that we just divide by this and then throw it in the numerator. So that means the 1 over 2I omega is a constant, so we could just put that with our minus 4 to the n. Yeah. Now we have this. Okay. Yeah, times and then we have our 2I omega that we got from dividing. But then we're also gonna, I'll use an arrow to indicate we're also multiplying by, so since we want an e to the 2I omega theta in the numerator, that means we gotta put one in the denominator or just use a negative exponent. So that means we have a minus 2I omega theta just sitting in here, which gives us this. Because these cancel out, that was the whole point. And then this. That's 4. Now let me just sort of circle this. This is going to be our differential element that we want to keep. Now, these two we can combine using exponent rules. So let's take care of that. Basically, it's just going to have an n minus 1. Okay. Now it is time to deal with this. So, as I mentioned before, if we make this the real part of e to the, e to the 2I n minus 1 omega theta, then all we get is basically another one of these terms, which squares it, and then you're not going to be able to compute a residue later. So here, this is where I was really happy with the little maneuver I found here, because this is a very important nuance. If you can't find this, I don't know a way you can solve this. But we use the fact that cosine is even, which means cosine of negative x is cosine of x. So that means if I just push in a negative, then what is it? It'll be the same value. Like I said, if we just put in a negative, it retains the same value because it's an even function. So that means this is the same thing as cosine minus 2 times n minus 1 omega theta, which now we can write as the real part of e to the I times this. Minus 2I, n minus 1 omega theta. And now you see the beauty of this, because these are basically the same exponentials, just this one is a negated version, or a negated exponent of that, which, as you know, will just make it cancel to 1, which is great. That takes care of our cosine, and it cancels out the pesky term we had left over. So that's pretty good. And now we're all set to make our substitution, because we have our differential right there. And what is it? I should say the real part is a linear operator, and so is integration. So that means I can just pull the real part outside. Yeah. Although, I'm trying to think. Yeah, I don't know if it matters if I'm supposed to do it at the beginning. I think I'm fine. Yeah, I didn't do anything wrong, I don't think. I'm just wondering if I'm supposed to put the real part at the beginning because we already have a complex, an imaginary unit out here. But I don't think it changes anything. I don't think it actually, it doesn't change anything, but I don't think it is technically wrong anyway. So I think I'm being rigorous. By the way, this is a bad d theta. Okay, so now let's replace z with this. So this gives us minus 4 to the n over 2i omega. Yeah, I'm going to have to erase the stuff up top, by the way. Then we have the integral. Not doing the bounds yet. So all of this... Oh, wait. I missed the real part. Okay, so we just have a 1. And then this is just going to be beta. And then e to the 4i omega theta is just e to the 2i omega theta squared. So this is z squared. We retain our coefficients. Still raised to the n. dz. Okay, now the bounds. So now since we're in terms of complex numbers, our bounds are no longer just going to be regular integral bounds, at least in this case, because if you think about it, look at this. So z is e to the 2i omega theta, and our bounds for theta were 0 and pi. So at 0, this was just e to the I0, which is right here. But then when theta is pi, that's still going to be 2 pi times omega, which is, as we said, we're treating omega as a whole number, so that's just some number of rotations back to where you started, which that doesn't really make sense if you think of traditional integration because it's not the same, it is the same point. So that would just give you 0, but this is complex stuff, so it's different. So, but instead of that, we can think of it like this. We have our contour, which is basically just a complex graph. So e to the 2i omega theta, or e to the I anything, its modulus is always 1. And since z is equal to e to the I something, that means the modulus of z is always 1. Meaning, we basically are just on a unit circle in the complex plane. So let me draw this, label my axes. Okay, and then we go counterclockwise, as always. Okay, yeah. So this contour represents all the z's that we could possibly have. By the way, let me make sure I'm still recording. Okay. All right. So now, basically here, traditionally you just name the contour and then label it here. Which this is a closed contour, by the way. So I can put this. But really, there's no reason to name it. We can just call the contour modulus z equals 1, because that's what it is. Yeah. Okay, so now, this is where, so we're here. I can erase all this. Now I have plenty of room on the left side. Okay, so now we have to consider what the argument of our complex number is, because we know that the magnitude of z, or the modulus of z, is never changing. So its distance from the origin is never changing, but its angle is. So a complex angle is called an argument. So when theta was 0, remember we said it was e to the I 0, so that means it's in the interval 0. And then once, theta was pi, we had e to the 2i omega pi, which is e to the I 2 pi omega. So that means the angle is 2 pi omega. It's kind of ugly. Remember, we treat omega as a whole number. Now, when evaluating a contour integral, it assumes that you're traversing the contour itself once. But notice, since our angle doesn't just go from 0 to 2 pi, it goes from 0 to 2 pi omega, where omega is a whole number. So that means we're going around omega times around the contour. So fortunately, there's an easy fix to that. All you have to do is just multiply by however many times you're going around it. So we just put an omega in the numerator, which, as you can tell, cancels out the omega in the denominator, which was kind of like one of the ta-da moments of this problem, because now it shows that as long as omega is one of, like, obeys this restriction, it doesn't affect the value of the integral at all. So this could be 1/2. This could be 2. It could be 69 over 2. It could be 420. It could be 1,000,000. And all those values would be the same, because omega has just vanished now, and there's nothing dependent on it anymore. Yeah, okay. So now this is where we use the residue theorem, which I can't really explain in depth, but all I can do is give a formula and explain briefly what it does. Basically, since you have a complex function, and when you integrate it over a closed contour, the residue theorem says that the value of the integral over the whole contour is equal to 2 pi I times the sum of residues at each of the discontinuities of your function that is enclosed in your contour. That's a lot of words, but basically what it means is you find the number of discontinuities in your function that fall inside the complex plane somewhere in your contour, and then you use a formula, which is just, you'll see it later, to find the residue at those points, and then you sum them all up, multiply by 2 pi I, and that's the value of the whole contour integral. Now, the whole contour integral is the sum of all the line integrals that compose it, but there's only one here, just one loop. Yeah, so I guess this is the point where we have to try to find the discontinuities of our function, which is just where the denominator is 0, and then find residues. So here, since it's a quadratic, we could just use the quadratic formula to find the zeros. So that's going to be negative b, which cancels out the negative from the thing that's there already. So it's 4 alpha plus 2 beta plus minus square root, and then the b here squared would be 16 alpha squared plus 4 beta squared plus, so 2 times 4 times 2 alpha beta, so that's just going to be 16 alpha beta. Then minus 4 times a times c, so that's 4 times beta, which is 4 beta squared, which, as you see, cancels the other 4 beta squared. Divide everything by 2 beta, because that's our a. So then we can rewrite this. That's 16 alpha squared plus 16 alpha beta over 2 beta, which we can now use the 2 in the denominator to cancel the 2's that show up everywhere. And we could pull out the 16 in the root to get a 4 on the outside, which becomes a 2 since we cancel the 2. Okay, and then let me write this a little neater. Yeah, okay. So these are the zeros of our polynomial, which let me, by the way, rewrite as, let me just, put the b elsewhere, just add it out here, because beta over beta is 1. So 2. Okay, so now we're looking for which of these, with the plus minus, falls inside the contour here, meaning modulus less than or equal to 1. So here, the best way to do this is to just think of alpha and beta as positive real numbers, which I don't think is completely rigorous, but I think it still works. Well, it definitely works. It'll give you the right answer, and the answer will be valid for all complex numbers. but I'm not sure how you're supposed to approach it. Like whether you, I don't know, because I think if you assume they're negative, you're gonna take like the other residue, and if you assume they're complex, maybe nothing changes just because modulus is always going to be within 1. Excuse me. But either way, I don't know if it's like the rigorously correct way to think about it, but it does end up working. Like you'll get a valid solution for all complex numbers if you just assume, like if you just think that alpha and beta here are positive real. So let's look. Okay, when you have the plus here, well, this is just going to be a positive number, and 1 plus a positive number will be greater than 1, so outside of our contour. And then if we have the minus, notice that this square root here is what's inside is greater than alpha squared plus alpha beta, right? Alpha squared plus alpha beta is greater than alpha squared. So that means this term right here is greater than 2 alpha, square root of alpha squared. So that means no matter what, 2 alpha minus something that's guaranteed to be bigger, guaranteed to be larger in magnitude than it, will be negative, even if you divide by beta. So that means 1 plus a negative number, that's the one that's going to give us, a pole in our contour, because then its modulus won't be greater than 1, or greater than or equal to 1. So I'm going to rename these for the sake of simplicity, because I don't feel like writing all those roots over and over again, as z0, like to indicate that it's a discontinuity. So z0 plus and z0 minus, just based on whichever sign they have. Okay, great. So that means we have one pole, that's what you call this, discontinuity. We have one pole that is enclosed in our contour, so that's one residue we need to find. So, okay. Now let me and basically the residue theorem is going to solve for this integral. Not like the whole thing, but just this integral right here. So I'm going to bring this stuff out front as well. So we have this. Okay. So now we have to use the residue theorem on this. What was I going to say? I was going to say something. Okay, no, I think it's fine. All right, so now we basically have to apply the residue theorem to our function here, which, just so you know, it has nth order discontinuities, because that means like x or z minus each of these poles shows up n times in the denominator, right? Just because, think of it, you factor this into something times z minus its zeros, and then you're just going to raise everything to the n. So just that product, you're going to have n copies of each of those terms. So, okay. Now, before I write out the residue theorem, I want to figure out how to factor this, because we know what the zeros are, and we know that those are going to be factors of our polynomial. So we know that z minus z naught plus times z minus z naught minus will appear in this term, but notice that our coefficient of z squared is actually beta, and here it's just 1, so that means all we need to do add a beta. So now also keep in mind that this is all raised to the n, and beta to the n would be a constant, so we can just put beta to the n over here. Yeah, and then we're fine. Okay, so now the residue theorem states that our total integral over the contour is equal to 2 pi I times the sum of the residues at each of the poles enclosed by our contour. So we only have one of those residues we need to care about. Like I said, that's z naught minus. So that's just going to be 2 pi I times that residue, which the residue for an nth order pole is 1 over n minus 1 factorial times the limit as z approaches your discontinuity, which in this case is z naught minus, of the n minus first partial derivative with respect to z. I put partial here just because we have like alphas and betas thrown around, so I thought that would probably be the right thing to do. So the limit of the partial derivative, the n minus 1th partial derivative of z minus your discontinuity to the nth power times your f of z. F of z is just this, which we already determined to be this, and we factored out the beta to the n already. So that's just going to be this. And remember, everything's to the n. But what's nice about this formula is that obviously the term you add to your f of z, especially if it's a polynomial, will just cancel out, its own copy of itself in the denominator. So we are just left with 1 over z minus z naught plus to the n. Okay, quickly, let's erase all this. Let's notice that the 2I is going to get canceled. And now since we have nothing that involves an I anymore, so nothing imaginary, that means we'd be taking the real part, or at least we can think of it as taking the real part of a real number, which is just a number itself, so we can make this real part vanish. Let me get some water. Okay, so here we are. Now we have to evaluate this n minus first order partial derivative, which honestly isn't that bad because all you can think about is just a linear term in z to some power. So that means all you have to worry about is potential chain rule, which there isn't here because there's no coefficient of z, and it's not to any power, but power 1, I guess. But and then yeah, you just have to use power rule basically over and over. So let's start from the fact, okay, let's rewrite this as z minus z naught plus to the minus n, because that's what it is. So by power rule, we're going to, each time we're going to be multiplying, this minus n plus 1, blah, blah, blah. So this is going to give us, let me first write all the constants. So pi, beta to the n, okay, then all right, now we got to figure out what this is. So every time you differentiate with respect to z, let me make sure we're still recording. Every time you differentiate with respect to z, you're going to get a minus 1 just from the exponent, right, by power rule. So that means you're just going to get minus 1 to the n minus 1. And then you're going to be multiplying the exponent as well. So we've already taken care of the negative, so we don't have to think about that. But keep in mind it's in the denominator. So it's going to be 1 over n, or 1 over something to the power of n, 1 over something to the power of n plus 1, da 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 da. So that's going to give us n times n plus 1 times n plus 2. But let's think where this is going to end, because obviously it's got to end somewhere. So the first time we differentiate, we get an n. And then that means we have n minus 2 times left that we're going to be taking the power that's there. So that means all the final terms, it's going to be n minus 2 terms if you don't consider the first one, right? Because that was our first, the rest of these. So basically all you can do is just, since you're adding to the power each time, all you can do is just add these, and then you're going to, at the end, the last number you're going to have multiplied is 2n minus 2. Like that. Which can be rewritten as, because obviously no one likes the dot dot dot, I'm not putting that in the answer. That can be written as 2n minus 2 factorial over n minus 1 factorial, right? Just by inspection. Okay. I did not think this through. I'm running out of room. Okay, so we're going to do this. But we're still going to be left with a term at the end, which is going to be this to some different power. But this is pretty simple, because all this is saying is that you're basically adding the exponent in the denominator n minus 1 times. So n plus n minus 1, you're going to get 1 over z minus z naught 2n minus 1. Okay, nice. So we figured out what that derivative was without, you know, sorry, it looks scarier than it is. You just have to like look at it and think. Okay, great. So now this limit works now because our function is no longer discontinuous at z equals z naught minus. So that means it's just going to equal this. Just plug in. And now z naught minus, if you look here, okay, or sorry, no. Z naught minus z naught plus, I forgot. So if you subtract this from this, basically everything else is going to stay the same. That means you start with a negative, and then you subtract the part where everything's positive. So these two terms are going to go away, but this term is going to get negated and doubled, basically, at the end. So that means you're going to have a minus 2 times 2 square root alpha squared plus alpha beta all over beta. So that means you have like this. Minus 4 because of the 2 times minus 2. All this to the 2n minus 1. Okay, so we can simplify this quite a bit. Let's pull everything out. So that means we have a minus 4 to the n times pi over beta to the n. Now the factor, okay, we have a minus 1 to the n minus 1, so that's minus 1 to the n minus 1 times, then you have 2n minus 2 factorial, and then you have 2 copies of the n minus 1 factorial, so that's n minus 1 factorial squared. And then you have this, which if you can just put this in the numerator, so that's times beta over minus 4 square root alpha squared plus alpha beta. All this to the 2n minus 1. Now technically this is like a valid answer, but I find this kind of gross just because there's a lot of ways we can simplify this. I don't like having multiple exponentials because I've already like found a way when I was doing this problem to write it all as one exponential, so that's what I'm going to do. Obviously make it a lot neater. But let's notice something first. We could pull out a minus 1 to the n from this, right? So just stick in a minus 1 to the n. We could pull out in the denominator, like even though it doesn't matter if it's in the denominator, minus 1 to the 2n minus 1, but it's easier to see if you do this. So then we have minus 1 to the n times minus 1 to the n minus 1, so that's minus n to the 2, minus 1 to the 2n minus 1, which is the same thing in the denominator. So you can just erase this. The alternators all cancel. Very nice. Okay. Now let's do something where I reduce this. So basically I'm going to multiply and divide by this term. So that means I'm reducing the exponent by 1, but I'm going to multiply a copy of it. Okay. So this will make this an n minus 1 in the denominator. This will make the 4 an n minus 1 in the numerator. And this is just n minus 1 times 2, but you can use exponent rules to basically raise this to the 2 and then raise everything to the n minus 1. So that means we just square everything on the inside and do this. The square root and the square cancel, obviously. But now this is to the n minus 1, and we also have some stuff to the n minus 1. So, for example, this b to the n minus 1 can get slid in here and cancel out one of the, sorry, not b, beta. One of the betas gets canceled here. And then similarly with the 4 to the n minus 1, it's going to cancel out a 4 in here. So 4 there. And now we're pretty much all done. We could just factor out some things. Okay, let me make sure I write this properly. Okay, so we're going to get... Wait, hold it. Let me explicitly write this out. Nah, I want to make this perfect. Oh my goodness. I'm telling you, I'm very picky about writing my final answer. It's got to look nice. Okay, so I'm going to put the pi and just the sort of scalar you can think of it out front. Just going to write alpha times alpha plus beta. Okay. Times yeah, 2n minus 2 factorial over n minus 1 factorial squared. And now here, I'm just going to divide the bottom by beta. Well, I'm going to factor out an alpha, then I'm going to divide everything by beta. So that's going to give me... Wait. Yeah. Wait, no, am I dumb? I don't need the extra parentheses. 4 alpha. So, because I want to put the exponent in the denominator, basically. I don't want any exponential in the numerator. So you pull out an alpha, that's going to be alpha plus beta. Divided by beta, that's going to be 1 plus alpha over beta. Then that's to the n minus 1. Okay. Is that it? Okay, wait, I can write that last parentheses, or parenthetical, whatever, better. Now that looks like an eta. Sorry, guys. Okay, I think that's fine. All right. Are we still recording? Please say yes. Yes. Oh, thank goodness. Okay. Let me compare this to my notes. Yeah, all right. Whew. Okay. That is the final answer, as you see. Took a while, but it's actually pretty nice. Like, it doesn't depend on omega, which was one of the cool parts. You've got an exponential in the denominator. You've got a factorial and then a factorial squared, which I thought was really nice. Yeah, typically when you're doing like these contour integrals, like when you complexify it and all that stuff, and you have something like raised to the nth power, you oftentimes do see factorials in here, just because like of that, n minus first partial derivative, you usually get like some sort of power rule which ends up with factorials. But yeah, it's pretty good. So, and if you notice, basically the whole integral, no matter how you parameterize it, and again, you can customize this like in so many ways. The point is, all you have to do is, if you have an integral that obeys this form somehow, like you could have, these set to like anything, as long as you can tell that it fits into this form with these variables set to whatever, you can apply this formula and get the answer to the integral, which also, if you just look here, is actually just pi times a constant, no matter what. It's sometimes irrational, like for example, if alpha and beta are 1, you're going to get a root 2 here, but also for something like 1/3, that's going to be like, okay, let's say you have a 1/3 and, like 1/3 and 2/3, I think. Right? No? No, anyway, okay, there's some combinations that can get you like a rational number, like, so there's nothing like that. I'm trying to think, what's one combination? It's definitely 1/3 and something. 1/3. I don't know. Anyway, you can play around with it. Like, you can go to Wolfram Alpha, plug this formula in, and like I said, even though we were assuming a lot of times that alpha and beta were positive reals, this formula holds for all complex alpha and beta as long as it obeys this. So I encourage you to, type this into Wolfram Alpha as well as this integral in like a separate tab. You can play around with the numbers if you're actually interested, and you'll see that they'll equal each other all the time, as long as you follow these instructions. Yeah, so that's pretty cool. I hope I did a good job explaining. I talked a lot. Hopefully you learned something from it. Thank you for watching.